Okay, so this is how it is.
Yeah, you know, nice.
You know, some things like this, sometimes you don't have to waste a lot of time in calculating the VA and the VB. You can you see that the system is symmetrical? I want to teach you a shortcut, but you will still solve it.
The overhangs of 2 meters each.
Yes. And the position of the support too. You can see the whole system. You can break the whole system into two equal faces, like two mirror images. Do you get it? Now that's what we call symmetrical. So if you have a symmetrical system like this, to save you time, what you can do is that you will definitely know that VA in the end will be equal to VB. Let's find this W. This W is 1.4 times the dead load, which is 30 plus 1.6 times the live load, which is 20. And that gave us 74 kilonewton per meter. So with this, you just have to, what I mean is that when it is symmetrical, you just calculate the total. You calculate the total load on the beam. And divide by 2. Okay, so with this, VA is equal to VB is equal to half times. You know, this is a UDO, and a UDO, to find the load, it's just by calculating the area under the UDO. So, you know, area is like a rectangle. So, something like this. And then the 74 kilonewton per meter is like the width. And the length here, you know already, is what's the total length, which is 10 meters. So with this, half of the total area of this is going to be what? 74 times 10. Is that correct?
Yeah.
Okay. So half of that is going to be what?
That's 370.
370 kilonewtons. This is one simple way of going about this. But there is another method too. That is the traditional method. You have to do summation of moments about A equal to 0 and summation of vertical forces equal to 0. So summation of moments about A.
So when do I get to find the moment of this? Your system, what you've been talking about.
This is the moment A. That's the length. Sorry, this is VD. So, you know, here is 74. We are taking the moment about this point.
But I'm serious.
Here is 6 meters. Here is 2 meters. Here is also 2 meters. And you have to know that which ones are causing anti-clockwise moment and which ones are causing clockwise moment. If you check this, we are talking about this. So if you check the VB, it is turning it this way, which is VB times the length or the distance from VB to VA, which is 6.
Okay.
Yeah. That is what's anti-clockwise. And what again is turning it anti-clockwise? This portion of the UDO is turning it this way. So plus 74 times 2 times half of the distance.
Over 1, yeah. Over 2, yeah.
You get it? So here is 2
Yeah.
meters. So half of that distance, that is where the centroid of the UDO will be located.
Okay.
Yeah. So what are we having from here? 6 VB plus this will cancel this time. This is 148.
Mm.
So let's calculate for the next rotation. I mean, we did for anti-clockwise. So let's do for clockwise. So with clockwise rotation, we are only going to have
74 times 8
the
times 8
UDL from
over.
here to here.
Mm.
So this part of the UDL is going to turn it this way. So that is going to be 74. Oh, sorry. My color is not good. So it is 74 times. The length is what? 8 times half of
Times
the
8.
length.
Mm. Okay.
So after that, you equate it to this. What are we having? So this is going to give us 32 times 74.
32 times 74, that will give us 2,368.
Okay. Let me clean it.
In the weeks leading up to this, Arsenal couldn't find a goal from anywhere. Now,
So it's going to, you said it's going to give us what? 2,000.
Oh, 74 times.
scoring by Raya.
2,368.
1-0 victory tonight, saving the other 6 goals, and perhaps any more to come.
Okay, so that's equal to 6 VB plus 148. So what is VB? VB is send this one to this side. It will subtract it. So 2368
That will
minus.
give us 370.
It will give us
370.
when you subtract.
Yeah. Then you divide by 6. We get 370.
Okay, sorry. So you've done the subtraction and the division already. That's good.
Yeah.
So fast. So you see, it has confirmed the answer that we got here.
Mm.
So going through this whole process and doing this simple, you have to choose your choice.
Mm.
But if you think you don't want any problem, I'm not forcing you to use a shortcut, because sometimes you might see a beam system and you feel like it is symmetrical, but it's not symmetrical. And when you go and apply the symmetrical rule to it, it will not work. Assuming spending the whole time and having your VA be wrong. The only place that you can know you are wrong is when you are drawing your shear force. So, I imagine by the time you get there, not time also. So let's see. VA and VB, we already know. We've calculated them. So here is 370. 370. And then 74. Okay, so we are now going to take the moment. This is where you like solving. So we have to first label them. I'm labeling them. Don't mind, because here is A and I'm labeling here A.
Okay.
Or if you get confused, let me clean it and make it something else.
Oh,
Because
don't worry. I understand what you're doing.
so here is
just
A, here is B, and here is C, here is D, and here probably that's the middle of
Okay.
this. Okay, so with this, the next thing that you are going to do is to determine your moments. So moments at you are going to calculate bending moments. So bending moments, we are starting from the rear end. So at C, we come to A, we come to E, we come to B, we come to D.
Okay.
Yeah. But this is simple. Do you see it? It's really simple. Now we don't even have to waste time calculating. You see, it's a UDL throughout.
Yeah.
Mm. So it's really simple. Let's just go forward. Oh, don't worry. But you know, we have UDLs here, you have UDL here. Let's calculate to prevent any confusion, because if you are doing that, it means that you have to calculate for here for you. Let's take it one after the other. So bending moment at C is going to be what? 0.
Yeah.
And you know why it's 0. When you cut at C and you take it to your left, it is 0. There's nothing there. Yeah. So bending moment at A is going to be what? Let's cut it here. So when you cut it at that place, this is what you are having. So if you are having this is how your moment is going to look like. And your shear force comes here like that. So the moment is in an anti-clockwise direction and your shear force comes down like that. Okay. So here we are taking the moment about this point. Have you seen it?
Yeah.
Mhm. So with this, what is going to happen is that here is 74. So the length is what? 2.0.
Yeah.
And it is causing the moment this way. Have you seen it?
Yeah.
Okay. So in that case, our M comes, which is anti-clockwise, plus the moment from the UDL, which is 74 times what? 2 times 2 over 2. And summation of everything should be equal to 0. So what is M? You have to send this one this side, and it is going to be 8. 148 minus, right?
Yeah.
Okay, so you keep this. Then the next one, the moment at C. Hey, sorry. We've calculated moment at C. We've calculated, so we have this value. Then we are here at E. Okay, so at E, what is going to happen? We cut it and take it to the either side that we want, because it's symmetrical over there. So when you cut it, here is 370. And if you take it to your left, you have your moments like this. If you shear force comes down, and here is 74. So what is happening? Let's find our M. So our M is anti-clockwise. Which one too is anti-clockwise? We are taking the moment about this point. That's where we broke it. So M anti-clockwise, and the UDL is also pushing it that way. Yeah, the UDL is pushing it in an anti-clockwise direction. This is it.
Yeah.
And it's only
The 370.
the 370 that's
That's
pushing it clockwise. So let's be quick about that. Okay. Okay. So I'm calculating it in the question. So we have what? We have our M to be anti-clockwise plus what's another anti-clockwise? The 74 times what is the distance? The distance from here to here is 2. From here to here is what?
3.
You get it? That is like half of the 6. Very good. So the total distance will be 5. Okay. So M plus 74 times 5 should be equal to
Would you multiply the 5 over 2?
5 over 2. Sorry. So this should be equal to the one causing the clockwise moment, which is 370 by what
Times
distance?
3.
3. So what is the moment? Can you see what I've written? Here is 74
Yeah.
times 5 times 5 over 2. So what value are you having?
For the M,
Yeah,
185.
185
Yeah.
kilonewton meter. Very good. Very good, very good, very good, very good. So yeah, that's M. M at C. So let's do for B and
That's
then
M. That was M at E.
oh sorry, M at
Oh,
C.
I'm
You
going to
see,
M.
I'm referring this to so it's E,
Okay.
sorry. It's E. So M at E, 185 kilonewton meter. Then we are at B now. But this is symmetrical. Well, I'm not going by the symmetrical rule because it happens once in a lifetime. You might not meet it. Do you understand what I'm saying?
Yeah.
Yeah. So because it's symmetrical, whatever happened here is the same thing that's going to happen here.
Okay.
But let's prove it. So you cut at that portion at B. This time, let's take it to the right and see how different it is. Do you get it?
Okay.
Okay, so here is D. Here is the B. The distance is what? 2. And when you take it to the right, this is how the moment shows. And this is how the shear force comes. So This is still 74. What are we having? So you
The
add
distance.
M. M is clockwise this time. Which one too is crossing clockwise? This we are taking the moment about this. It's
Yeah.
here. So if M is clockwise,
And the
take
74
the
is also.
yeah. So 74 by 2 by 2 over 2. You see that then?
Yeah.
Equal to nothing
Yeah.
because here there is no support. This is D. This is not a support. Nearly scared me. So M is going to be what? Minus 74 by 2, which is minus 148. Is that correct?
Yeah. Yes.
Very good. So this is it.
The Tasmanian devil is in the building.
Okay. So we are done calculating all the moments. It's left with drawing the bending moment diagram. Is that
Any
correct?
moment.
Yeah,
Okay.
this is it's simple. It's simple. And I told you
Hmm.
earlier that whenever you are drawing the bending moment diagram, a UDL means it's a curve. So if you have a UDL between point loads, it's a curve. And if you have nothing, it's a line, a slanted line. Okay. So what do we have here? We have to draw the beam and locate. Here is it was C. C
Yes.
is A, E.
B, and then D.
Okay, so at C, the moment was 0. At A, what is the moment at A?
It was minus 148.
So minus means it will come down.
Yeah.
Minus 148. Okay. At
E,
E, it was
185.
185. At B was minus
Yeah.
minus 148. And at D, 0. Hey, I didn't calculate for at D.
No.
At D. So at D, when you cut and you take it to your right, it is going to be 0.
Yeah.
So this is what we have. This is what we have. So bending moment diagram, because I told you that when you are joining them and you have a UDO between them, they are going to be what? Curves.
Yes. Yeah.
Yeah, so from C to this place is a curve. Isn't it? From
Okay.
this to this is a curve. Because there are UDLs in between them, that's why. From here to here is a curve, and lastly from here to here is a curve. Nicely done. Oh, it's not nice.
Oh, it's nice.
If you do something like this, at least you get your 10 marks. So quickly, let's keep the values and move on.
Okay.
So this is the sagging, the 185 kilonewton meter. Sorry, meter. The bomb. So this is the maximum sagging. You know, positive moment is the sagging, and the negative ones are the hogging.
Oh, okay.
Minus 148 is the hogging. So keep the value somewhere. You're going straight to solving the rest.
Okay.
The person that drew this thing there
I'll bet
means that
you. Really? Hey, Sebo. Hmm.
Uh, it's all part of the process.
I'm praying that I wash my hands off this paper and
Everything will be fine. So quickly, let's do it. Can I clean it?
yeah.
Okay. So we have now the ultimate bending. Ultimate bending moment to be equal to what? Was it 185 kilonewton meter?
Yeah.
Hey, but we didn't do the shear. God,
Yeah.
keep the value somewhere, and
Okay.
let's do the shear first.
Okay.
It's easy. It's easy. It's easy. It's easy. It's easy. RCD made easy. RCD there. Then at the bar, well, RCD. He gave us some work. A fair squeeze.
I was it Jones that taught you.
Dr. Jones. But the quiz, Charlie, the quiz was difficult. But the quiz, I went to him to discuss like my answers be with him. I was like, yeah, it's correct, it's correct. That's when he began to trust me. Charlie, I see, I understood it from the beginning. Just that sometimes when I'm solving, before me, so now me join him to be.
So you were in the same class with what is his name? This guy. What? I'll call you two knows. I'm a friend of him.
Hey, don't mention his name here. I'll send the I'll send the video to my this one. Yeah, we are in the same class.
Oh, okay. She didn't be doing that. You need help.
Oh, don't mind. Okay. So here was what value was it? 370.
Yeah, 370, 370.
Okay, very good. So here we are going to calculate for the we are going to calculate for shear force.
Okay.
And as I've told you earlier on, we take the shear force from left to right. First, excluding the force or load at the point. Second, including the load, the points. So very quickly, let's move on. So shear force at C. Here C, A, E, B, D. Shear force at C. And this formula that I've taught you, whenever like if we wake you up in the middle of your sleep, you can do it. Don't think too much. If the question comes and if it's only when it's continuous beam, like you have three supports, that's when it doesn't apply. That one you have to apply uh, those rules in the code book. But if it is two supports, simply supported like these ones, then just go by the simple method that I've taught you. Focus. Know which one is causing anti-clockwise movement, know which one is causing clockwise movement, and you are good to go. Okay, so shear force at C, first excluding everything, 0. And you see, at C, we don't have any load here.
Yeah.
We don't have any, like, I mean, any
Support.
support. So you will take only one shear force value.
Okay.
Because if you decide to include, what are we including? The above.
It
Do you
means the
get it?
UDO that affects that side in any way.
No, you see,
Okay, it's
there is no force, if
support.
there were to be a points load here,
Okay,
you see, I've written a points load.
okay,
Points load. I didn't write a UDL, so you have to take note of it.
okay,
Mhm. So if there were to be a points load at this end, that's when we would include it. But there is no points load, so you just exclude it and move on. So shear force at oh so shear force at A. We are moving on. What is that going to be? You have to, you see, there is a load here. So we will first exclude the vertical point load and then look from our left corner. So what are we having from there? That's it is minus 74 by the length there is what?
Hmm.
2. So by 2 by sorry, I was going to multiply it by 2. No, shear force is a force. Do you get it? So minus 148. Shear force at A prime. At A prime, it means that we are including the load there. So it is
yeah,
this 1 minus 148 plus the load.
3 seconds.
What are we having?
Two, two, two.
222.
Yeah,
Shear force at E. Oh, that one no, we won't take shear force at E. We don't have any discontinuity there. You mostly find it at a point of discontinuity. Do you get it?
okay,
Mhm. But there is definitely a shear force at E, but it's not a point of interest to us. So let's move on to shear force at B. That's without including the load there. So if
okay.
you don't include the load there, what are we having? We already have
One coming from here.
the ones coming from here.
Hmm.
Do you get it? So we would have to add this to it. Have you seen that?
Yeah,
So this is 222 minus, that place is 74 times. What length is that? The length from here to here
6.
is 6. So what are we having?
Yeah, minus 222.
Okay, so minus 222. Then shear force at B prime. At B prime, we are including the load. So minus 222 plus the load there is what?
370.
370. So what are we having?
Positive 148.
Then lastly, shear force at what? At D.
Give you 0.
It's 0.
Huh?
It's 0, but let's prove it. Why is it 0?
Okay.
So we've calculated all these ones. It's left with what? This one.
Mm.
So it is 148 minus 74 times what? 2.
Okay.
2 meters. Do you get it?
Yeah.
So it will go to 0. So let's draw quickly the shear force diagram. So at this part it is 0. At this end it is 0. Here is what? C.
Mm.
Here is A. Here is E. It doesn't really matter. Here is B. And here is A. No.
Yeah, that's
Okay. So CAEBD. Let's go. At C, we calculated it once. At A, what value did we get?
minus 148 and 222.
So let me clean here so that the many moment diagram comes, the shear force diagram comes in. It won't really affect. Okay, so minus 148. Then at A prime, it is what? 222.
Yeah.
It's at the same point too.
Yeah.
Then at B, 444. Or A,
At
sorry.
at D, at B,
Yeah,
B minus 222.
minus 222. And then here is 0, right?
The B is minus
B prime.
222 and B prime is 148.
This one too is 148.
Yeah.
Okay.
Minus
So
222 then positive 148.
okay, so you know how we do it. For shear
Yeah.
force diagrams, when you see a UDL, it turns a slanted line or a diagonal line.
Okay.
So because there is a UDL here, it will join this way, but there is no UDL. It's a point load to go this way. Here to come this way. Here to join that way. Here to join this way. Is that correct?
Yes.
So here is 0. Here is minus 148. Here is 222. 1480. So the maximum shear force is what? 222 kilonewtons. Okay, so can you keep the values and move on?
Yeah.
It's almost 10. God, I've plenty
But
things
that's
to
it's
plenty.
10:17.
Yeah.
You have to sleep now.
No. Hey, I'll sleep around 3:30 there.
Why?
I have reports to write for people and other things. And
Oh, okay.
yeah, my personal stuff too. I don't sleep early like that. Yeah, it's part of me. Okay,
And how work in the morning?
yeah, I'll go to work at 8 a.m. sharp.
Oh, okay.
But sometimes I'll go early and sleep there rather than be late. Okay, so ish. What am I sharing? Oh God, where did I press? Okay, so can we move on?
Yeah.
Okay, very good. So you have the values already. Now we are designing for bending moments. moment is you have to first find the K, BD squared over FC. And what did the question say? It says we should do what? The one I sent to you, the Midsem.
It says design for ultimate sagging and hugging movements.
Ultimate sagging.
Yeah, and hugging.
But no, I want the part that you say a rectangular something.
It's a rectangular section at supports B equals 300 millimeters, H equals 500 millimeters, and flange was
Wait, the breadth is 300.
yeah, the breadth is 300 and the height is 500.
And I think this is the flange, 2,300.
Yeah, the flange with 2,200.
It's what?
The flange FW 2,000 and BW is 200 and the H is 500.
The flange FW is 2,000 and then come again.
And BW is 200.
200.
And yeah,
Okay.
and H is 500.
Okay. But what he said we should design for ultimate sagging and hugging. Is that not it?
Yeah. Then you check deflection at midspan and design for maximum shear force.
Okay, it's not difficult. So we first have to know whether the beam. Okay, so let's first design for the sagging moments. So in designing for the sagging moments, you choose a flange because the sagging moment was it was in the middle, right?
Yeah.
It was like this. So here, when you cut this section, this is how it looks like. But when you cut it at the support here, it's a rectangular section.
Okay.
Okay, so you have to design it. You have to design two things. You are designing for a flange, this one, and you are designing for a rectangular.
Mm.
It's really packed. Uh, the process is it's not difficult. It's not difficult at all. Very good. Let's go on. But since I've cleaned it, maybe I might need it this one again, but not now. When I need it, you provide it for me. So the key, if it is
I do.
flange, then you have your moment, you have your breadth of flange, your D squared, your FCU. Your D is the effective depth, and the effective depth is the overall height minus the cover minus the diameter of the bar over 2 minus diameter of the link over, sorry, not over anything, minus the diameter of the link. Let me demonstrate this to you and to all my viewers. Sometimes people get confused with that thing. This is how the arrangements looks like.
Is it the evaluation?
And we have the bars here.
Yeah, I think so.
Oh God.
Was it in the since
This is too small. Let me draw my own and make it
Okay.
big. So have something like this. So what you have here,
after 12 will be available after 12.
okay, so this is how it is. And the effective depth is from the top here to the middle of
Mhm.
Yes.
to the middle of the bar, the reinforcement, the main bar. This, have you seen it?
Yeah.
So because we have it like this, and we want this length, that is the D, and we have
Okay.
already been given the overall height.
All right.
What we do is that this is the cover,
Mhm.
this is the stirrup,
Oh, okay.
and this is the main bar.
Okay.
Do you get it? So you
Yeah.
take half of the main bar, which is
Mhm.
this, and
Oh,
you
okay.
take, and these things, they are together, like the cover and I'm sorry, the ring and then the main bar. There is no space that like what I've drawn.
Okay.
So you take the cover, the main half of the main bar, then you take the stirrup out, then you take
The cover.
the cover out. So that is what, so this H that you see is here. Do you get it? So when you
Yeah.
take half of that diameter, the stirrup, and then the cover out, then you are going to get the effective depth. So that is the explanation. Even if you don't have the formula in mind, you can still find a way around it. Is that okay? So the overall height has been given as 500.
Mm-hmm.
The cover, I think, is 25 minus the main bar diameter is what? 20. In the question, it says use 20. They said a similar question, so we just, so it means 20 over 2 minus
10.
10.
10. Yeah.
So what are we having here? 500 minus 25 minus 10 minus 10 minus 20 minus 45
455. 455.
455 mm. Okay, very good. So D is 455 mm. So let's put it there. And BF is the breadth of flange, which is 2000 mm. So let's do it quickly and calculate for K. K is the maximum, the moment is 185 times 10 to the power 6 over the BF, which is 2000 times the D, which is 455 times FCU is the strength of the concrete, which is 40. I don't know. Did it change in the parameters I sent you?
No.
Okay. So do this for me. And let's calculate the K. So this K, after we are done, if it is less than 0.156, then it is singly reinforced. If it is more than 0.156, it is doubly reinforced, but we will keep 0.156. So the value of K doesn't exceed 0.156. If it exceeds, you use 0.156. You get it?
Yeah.
Yeah, that's how we do it.
There's 0.011.
0.011. So obviously
Yeah.
it is less than 0.156. So singly reinforced. Is that okay?
Yeah.
Mhm. So having gotten that, then the next stage is that
Yeah. Yeah.
You know, the ultimate goal is to calculate for our AS, which is what?
Yes, yes.
M 0.87 FYZ. So I always admonish that you put this down so that it constantly
You know the
reminds you of
parameters.
what you need. So this thing,
Okay.
I don't keep it. I don't keep them in my head. It just come. It's been some time now since I even revised.
Hmm.
D is 0.5 plus 0.25 minus K over 0.9. Okay. So let's find the Z. Or, we compare it 0.95D to take the lowest.
Okay.
Yeah. So Z is D multiplying 0.5 plus square root of 0.25 minus K over 0.9.
So give it an unless to one thing it's
Yeah. So
I can say it's and
Where you putting this thing? I'm not seeing it well. You say Z equals D into brackets 0. Okay. 0.5 plus square root of 0.25 minus K over 0.9.
hello, what did you get?
Yeah, I'm on it. I'm coming. I got 389.935.
Hello. Oh,
Yeah, 389.935.
389 points.
935.
Okay. Okay, very good. So this is Z or 0.95D. So check and give me which one is the lowest.
0.95 will give you 432.25.
432.25 mm. Okay, so this is the lesser one. So we choose that one.
Okay.
So use that to find your AS, your area of reinforcement.
Okay.
So it's going to be the M, which is 185. Okay. So we have 185 times 10 to the power 6 all over 0.87 times Fy is, Fy is the strength of the steel, 500. And then Z is the one we just calculated, 389.935. Yeah. So what is the value of AS? Yeah.
One 1090.662.
So with this, if you want to get the number of bars, what do? You divide by area of a single bar. So a single bar is what? What's the diameter of the main bar? I think 20. So 20 squared. So what are we having?
What 3.472?
What's it say?
3.472.
3.472. So this is
Yeah.
approximately like 4 bars, right? 40, 20. So this is 40, 20.
Okay.
Okay, so maybe if you are asked to draw the cross section, we just put a nice sketch. So 40, 20. There's it. So we are done calculating for the sagging. So it's left with the hogging. So with the hogging, we need to also calculate for a K.
But we use the same process, right?
The same process. The same process.
Just different parameters.
Yeah. It's not even
So I think
different. With
yes, so
different moments.
the moment is only the 185 that will change to 148.
Yeah. So you
Oh,
let's
okay.
start something because I need to do other things as well.
So over number.
So rectangular beam. I say here is 200.
Yeah, 200.
500. Okay. So what do you call it? The D will be the same.
Yeah.
To be what?
The
455.
effective 455.
Yeah. And then what's next? K, your K, M over BD squared FCU. The moment, what's the moment for the
Minus
sagging?
148. It was minus
Minus
148.
1.
148.
Another a year.
Okay.
48, yeah.
Oh, it's
And then the B, you use B of this.
Okay.
He likes it.
And the D is 455 squared times FCU is FC is 40.
40. Yeah.
Yeah, so calculate it and let me see.
Something like this.
Okay, so with the hugging, we are designing for a rectangular unit.
Yes.
The other one was a flange.
Something in
Yeah.
one of my then so why not abode in the end of but sometimes the woman she will say, oh, when one of the gentlemen was able to help me, and even made us know that we were coming out to be the very, very great people in future, because when someone was trying to think
Okay.
everything,
So
to stand in and prevent this from happening. Oh, it was wait.
You get minus 0.089.
the minus is just signify that it is working.
Oh, okay.
So 0.089.
0.89.
So this means it was singly reinforced.
Okay.
So with this being singly reinforced, then that is the K now, 0.089. So you go through the same procedure to be able to find your AS. Please, is that okay?
Yeah.
I hope it's not difficult. Yeah. So when you are done, maybe you get 4 bars or you get 2 bars. I don't know. You put it there. That's all. So you end the class here.
Charlie, but we never tackle share forces for us. So tomorrow we'll do that one.
We've not
We've
done
never
share forces.
actually tackled.
Oh, then
I mean,
let's do share forces. Let's do share
because
forces.
we always do the movement, you don't do the share force. And your explanation said the share force was not in the video.
Oh, okay. Let's do the share force now. Because
Mm.
it's like always, this is the first one we do. So by the time you get
Yeah.
to the share force, you are tired.
Mm.
So I'm cleaning everything.
But even if you have things to do, if you can meet tomorrow and tackle that one, I don't have any problem. We understand.
Okay. Then let's do it
Yeah.
tomorrow.
Yeah. So that one will be like from the start, we'll deal with that.
Yeah.
All right.
I'm looking there. It's me.
Okay, bro. Thanks a lot then.
You're welcome, bro. You're welcome.
Yeah, I'll do this thing for you. So we'll talk.
Okay, bye. Good night.
Let's